Okay, I think we are still waiting for camera to switch over this side. So it's okay. So maybe this one I have to change maybe. That switch is on. This power plug went out. This plug. Okay, so okay, let us start the next lecture in our lecture. So we started with, I'll just write it here, Ohm's law. So that is V equal to IR. Okay. So voltage is current into resistance. That was our starting point. Then what you did after this based on Ohm's law? Okay, so we see something mesh analysis and then node analysis. But actually this is not directly. See, from Ohm's law we can get Kirchhoff's current law and Kirchhoff's voltage law, which is nothing but another way of expressing or extension of this one. So Kirchhoff's voltage law is used here, isn't it? In fact, both are used in both cases. So you first use KVL, then KCL, and first use KCL, then KVL kind of thing. These two are used for these two. And maybe I'll just put things like this. So what did you do next? After mesh analysis, node analysis, you can also do one more thing by Ohm's law or anything, that is your series parallel circuits. So if a circuit is given and then the resistances are connected in parallel, so it's application of KCL KVL to define effective resistance. So in two resistances are in parallel, effective resistance. So for that you use KCL KVL to derive the formula for that. Okay. I think you already know. So in series it is just addition. In parallel it is R1 into R2 divided by R1 plus R2, or if there are more branches, 1 by R1, 1 by R2 and all these things. You know that. Now based on all of this, next what we did was something called superposition theorem. So what is superposition theorem? In the you can do, see, this is not required. Just with mesh analysis you can solve. A circuit is given to you, given any circuit, you just can solve it. Is another way of solving it. So two methods of solving the same circuit. In fact, we did that. We used the same circuit and then solved one with the mesh analysis, solved with the node analysis, and solved with the superposition theorem. All the three times the same answer we are getting. Okay. So what is the superposition theorem? If there are more than one sources, so take one source at a time. Other sources, if it is a voltage source, short circuit it. If it's a current source, open circuit it, and then solve it. So that was superposition theorem. And then we also saw Thevenin's theorem. So what are these? So maybe I'll just put all, like, it's all, all of these are kind of used for going up. So in Thevenin's theorem, what are you trying to do? So it is more like finding an equivalent, given a 2 points in the network, between the 2 points if there is a load resistance, you just take it out, and then the rest of the network, it may have 10 resistances, 3 voltage sources, or whatever. It may be any complicated, complex connections. Finally, you replace it with what? Yeah, with one voltage source and one resistance. That one voltage source is VTH and one resistance is RTH, and then you connect back your load resistance, and then you are trying to find it. So what the Thevenin's theorem is saying is, a given circuit can be replaced with one voltage source and one current source. Okay. Is it absolutely important to remove one load resistance and then do the Thevenin's theorem? Without removing, can't you do? So it's just a like, if consider there's a network like this, so maybe our same network. So don't worry about the connections or anything. In fact, I even changed the somewhat network. See, now if I want to apply Thevenin's theorem, then is it absolutely required that I have to say this is my load resistance? Like, let's say this is my load resistance. Then I remove this and then apply Thevenin's theorem. Is it required to remove one resistance? So it's not actually required to remove a resistance. It's just for our what you call explanation. We are doing it. See, there can be a resistance. Okay, so now question is this a node? That is a node because these two are connecting. This is a node. Let's call this node as A. Is this a node? That's also node B. Okay. Now I want to apply Thevenin's theorem. Okay, considering A and B, and then I want to get I want to get one resistance RTH and then one voltage source plus minus VTH. Okay, I want to replace this circuit with this circuit. It's still Thevenin's theorem. So it doesn't matter whether, maybe there was a resistance. See, before I draw the circuit, maybe there was a resistance and somebody erased that resistance. Now I'm coming here and then I'm saying, okay, AB. So it's just a matter of thing. It's not important that you have to identify this is a load resistance and then remove it or anything. Okay. I hope you are seeing the point. Okay. So you can replace this entire, two sources, 1, 2, 3, 4, 5, 6 resistors with one resistance and one source. Okay. You can do that. But how much current will flow in this? So there is no current flowing from A to B directly. Okay. And then here also no current will flow. So you can use it to answer a question like, what will happen if I connect a 2K resistance between A and B? How much current will flow in that resistance? If that kind of question is there, then you can do this and then do that. Anyway, that was just a side this thing. We'll come back to this. So today we'll just quickly see one more theorem, that is maximum power transfer theorem. Okay, maximum power transfer theorem. See, just by mesh analysis, you can solve any circuit because it's just this one. Why we are learning other things is just to because these are all more famously known and everybody is studying them. We are just doing that as a additional this thing. But if you know only mesh analysis, also fine. You can live your life as solving the circuits. Suddenly a circuit will come, I cannot solve it. So it is not possible. You can solve like if it is based on resistances and voltage sources. Current sources we are not done, maybe we will do it in future. But any simple circuit like that, the size may be 10 nodes or size may be 100 nodes or 1000 nodes, whatever. If just by mesh analysis you can solve it. We are just doing the other things just to increase more understanding of it. Like that, there is a power transfer, maximum power transfer theorem. Okay. So to see this, let's just go back to our regular the one which we selected out of lakhs of different options. We selected one circuit, so I'll just draw that. So can you tell me the values? I just remember this thing. I think this was like this, then this was like this. This was 2K, I remember. 3 volts, 3 volts, 4.7, and this was 2K, 3.3K, 8.2K. Okay, so this was our circuit that we were studying, and it's very quite familiar to us. Okay, maybe quickly we'll repeat the quick experiment that we did last time. That is, consider this 2K as the load resistance and find out what is VTH and RTH. Okay, so what will I do? I just remove this, and then let's call this A, B, and then 2K is here. Okay. So now I want to replace, I want to replace this with so this is RTH and this is VTH. Okay, so what is the values of these two? So you can actually check your notes and tell it, but then we'll just maybe connect it quickly and then see it once again, just for familiarity. So maybe you can just look at the circuit here. So this is 3, 2, 8.2, 4.7, 10. This one. And then this 2 is not there. So we got all the, even this 2 I will remove it, but for the timing let it be there. So next connections are voltage sources. So this is a 3 volts voltage source. I'll just connect it here. Okay, so the black one is a negative terminal. So where should that go? Negative terminal is directly here, and this is the positive terminal. So this one we were connecting somewhere. I'll just extend it. So these two should connect actually. So I'm just becoming okay. I think so. It's a long wire. So we had connected this voltage source. Then between these 2 points, we have to connect the other voltage source. Okay. So let's do that. So the positive one will go directly here, if you follow the circuit. So this is the positive connection directly coming here, and this negative one should go up to here. So I'll just extend it maybe from here up to here. So this is exactly the full circuit. So now so the next step is I remove the load resistance, okay, and then we measure the voltage. Okay, so I am using this to measure the voltage. So the voltage is measured between, so A is positive, B is negative, so I am just measuring that way. Okay. So the value that I am getting is 5.513. Okay, it's in volts. So is that the same answer we got last time? Same answer. So this is 5.513 volts. So if I give you two 3 volt batteries, this is 3 volt, this is 3 volts, and then ask you to make a 5.5 volts battery, you can make it using this circuit. Okay, so this is in volts. So let's call it just 5.5 volts, or okay, let it be full. So what about this RTH? How do you measure the RTH? So you short circuit all the voltage sources and then you measure the resistance. Okay. So how to short circuit the voltage sources? So I just disconnect the first voltage source, okay, and then just replace it with short circuit, okay, and then I disconnect the other voltage source, and then I'll simply short circuit. Maybe I'll just short circuit like this, okay. Now if you see, it's completely, so what is the voltage you're getting? It's almost 0 volts, okay. So obviously the voltage will be 0 because we are not connecting anything. So I just change the setting to ohms, okay. So how much ohms you are getting now? 4.167 kilo ohms, because you can see the unit also there. So I'll write it that. So maybe I'll write it here. 4.16 kilo ohms, okay. So RTH. See, right now here, because I have the circuit, we are just connecting, measuring and doing it. If that is not there, you should be able to calculate it. Okay. You should know how to calculate the RTH. Okay. So how to calculate the RTH? Short circuit this, these two become parallel, then you calculate the value of that, then this one and this one will become series, then calculate the total addition of that, and that whole branch becomes parallel with this, then calculate that. Finally you get answer 4.16 kilo ohms. Okay, now what I want to do is I want to measure the power. Okay, so how to measure the power? So what we'll do is we'll make a quick table like this. I'll not do it on board. I'll just do it on this one, because it's a bit of calculation. But just I'm giving this one. So what I want to do is I want to measure the current in the load resistance IL. Okay, and I want to measure the voltage of the load resistance. Okay, for different values of R. Okay, so what I'll do is I'll put a variable resistance. The resistance I can change it. Okay, so I'll show it to you. So what is the current into voltage? I'll get the power of the So this is power in that load resistance, and then the load resistance value itself, because I'm changing that value. So how to calculate the load resistance value? Simply voltage divided by current. Okay, because it's just Ohm's law. So this divided by this, I'll get the value of RL. So what is this is VL divided by IL. And what about the power? So VL into IL. Okay, so just I can also do IL square into RL, whatever. So I can do that. So this one I'll measure, this one also I'll measure. Okay, so let me just set up this. Now what I want to do is I want to find out for what value of R the power is maximum. Okay, let's do two extreme cases. Okay, R equal to 0, RL equal to 0. Okay, I short circuit this. On the x-axis I have RL, on the y-axis I have PL. Okay, so we are at this point RL. So if I short circuit it, what is the voltage? So voltage is VL is 0, so RL is 0 and P also is 0. Okay. And if I open circuit it, RL equal to infinity, open circuit, okay. Extreme case. Okay. In that case, what is I? I is 0, therefore P is also 0. Okay. And here RL is infinity because IL is 0. Okay. Denominator 0. So it will start from 0 and at the infinity it will go to 0, something like this. Okay. It will touch 0. So in between it will reach some maximum value and then go to 0. Okay. So the objective of maximum power transfer theorem is to find out what value of RL will give rise to maximum power. Okay. So let's do that then. So I'll connect back the voltage sources because we are doing in that. So I have just connected back everything. So you can see right now the voltage is 5.51. Actually it is showing minus 5.51 because I think B is positive. Okay? B is positive and A is negative. So strictly speaking, so let me just correct this diagram in that case. So I'll just write it A here and B here. But it doesn't matter because we are doing it in the both ways. So now what I'll do is I want to measure both current and voltage. So at a time. So I will use 2 meters. Okay. So I hope we have placed somewhere here. Okay. And then the current and voltage. Okay. So you can see here this is the variable resistance. So there is this knob kind of thing. You can turn it to get different values of resistances. Okay. So I will connect in the place of load resistance. I will connect that. But then in between I want to measure the current also. So what I'll do is, so I'm connecting the load resistance here, maybe like this. And then at this point below I'll connect the ammeter. Okay. So which I am doing right now. So this is the ammeter. Okay, so the current is 1.33 milliamperes. This is what? This is short circuit current. You remember last time when we tried to do. So I think this one is set to very low value, so almost equal to 0. So it is short circuit. So current is 1.33. I think I'll leave it here. And if I make it extreme the other case, the current is how much? 0.36 milliamperes. Okay, so maybe we'll start our calculation with that. Now I want to measure the voltage also. So what I'm doing, I'll just connect voltage here. So this voltmeter is connected directly across the resistance, the variable resistance. Is everything all right? Okay. So now you can see two numbers on screen. I hope so. Let me just turn it slightly. Okay. So we have two numbers you can see on the screen. Okay. So on the right side you see the voltage. So what I have done, maybe this may be little confusing. I'll just take 1 minute or 1 second to draw this thing. I put a, so this is B, this is A. I put a variable resistance, and then this is my voltmeter, and this is my ammeter. Okay, I am measuring these two, current and voltage. Okay, so I'll switch between this thing. So I have opened an Excel sheet. So the same table I'll make it, IL, So this is IL and this is VL and this is RL and this is PL. Okay. I hope you can see it here. 0.3 milliamperes. Okay, you can see in the current there. So 0.3, and then the voltage is 3.336 volts. Okay. Now what is the resistance? V by R, V by I. So this divided by this. But current is in milliamperes, therefore resistance will be in kilo ohms. Okay. So I'll just mention that here. Kilo ohms. Maybe capital K. So this is in MA, milliamperes. So this is in volts, so I am not mentioning. So what is the power? V into I. So this into this. Okay. So this is milliwatts. MW. So how much power is there? 1 milliwatt of power is being consumed by the load resistance. Okay. So now I want to try different values. So maybe I'll just turn this a little bit. So I don't want to be exactly accurate, so it's okay. I mean, because anyway we are doing this 2.855. Oh, sorry, I did not show you this. So the current is about 0.4, and then this one is 2.855. Okay, so I'll just correct it 0.4. So I'll just copy this. So the same formula gets copied, and then this also I'll copy it. Okay. So now the power is increased 1.14 milliwatts. So slightly the power is increasing. Okay. We'll see if it is increasing further. Oh, sorry. Oh, I turned in the other way. Okay, so what is the current now? 0.5 milliamperes and then 2.312 volts. So let me speed up. I think you got the idea what we are trying to do here. I'm just copying the value. So now the power is slightly increased, 1.15 milliwatts. Okay. So let's do 0.6. I'll go back. So you can see 0.61 and then 1.721. Okay. What do you notice here? While the current is increasing, the voltage is decreasing. Okay. And the power, what happened to the power? The power has decreased. Okay. So because I want to find the maximum value of power, I need more data. Okay. So somewhere it is between 0.5 and 0.61 current. Okay. So I'll just move this somewhere down. So maybe here 0.61, 1.721. Okay, I just copied the row. So then I'll try something like this. 0.52, 0.54, 0.56, 0.58, and then 0.6. I'll try to do that. So let's set the current 0.54. So the current is 0.54, the voltage is 2.07. Okay. So, we have to correct this one. Huh? this is still, let's do 0.52. I'll go back. Oh, it's already 0.52. So 2187. So what is happening to the power? So it started with 1 milliwatt, increasing, then again it is decreasing. Then these two values are all, not so useful, because I was trying to find at what value it is maximum. So let's look at this RL value itself. I'll just make it into, okay, so these are all in kilo ohms. Okay, I just rounded it to 2 decimal places. So can you guess at what value will the power be maximum? So I hear some answers. So we know that RTH is 4.16 that we have written there. So maybe if this value is 4.16, then I'll get the maximum power. Okay. So we can do it, but then we'll not waste time on doing it. So maybe I'll just delete these 2 rows. Just for completion, I'll just do one more reading. Let me go back here. Let's do a jump. How much is the current? 0.94 milliamperes. 1.2. It's actually 1.2 millivolts. Okay, it's almost. Let's go back then. Let's do. So I've set to 0.74 or something like that. 1.07. So I can just simply make a plot of these 2 values. So I'm getting something like this. X-axis is the resistance. And reduce the size of this. X-axis is the resistance value and Y-axis is the power value. So at one particular value of this one, it is maximum. Okay. So that's about measurement. So let's simply quickly derive also some, just to say that when the value is equal to RTH, it is maximum. Okay. So let's come back to board. Now forget about that circuit. Maybe I'll just remove that. So this is RL. Okay. So instead of VTH, let me call this VS. And then RS. Okay. So in other words, source voltage and source resistance. And then the watt value of RL will give maximum power. Okay. Same calculation. Current is nothing but VS divided by RS plus RL. Okay. And then power is nothing but VS into I. That is power. Okay. So that will be VS. So sorry, what is power? So power is I square RL. Okay, the square of this. So VS square divided by Rs plus RL whole square, isn't it? Into RL in the numerator, correct. Okay, so this is power. Okay, so a small this manipulation, just RL you take it to the denominator. Okay, so it will be again like this. Is that correct? So from the numerator, I am taking 2 steps down. Okay, it's just that one. Then you take it inside to the square. Okay, so if I take it inside to the square, then there will be a square root on this. Okay, is that correct? Now divide it for both, this, because this is plus. So Rs by RL under root, and then this will be 1 by RL under root or something like that. Okay, so I'll just put it like this. Okay, is that correct? Oh, this is root. So now this we can cancel. It will be like this. Okay. Now I want maximum power. Okay, the power will be, see, this is constant. So the power will be maximum when the denominator is minimum. Okay, so this square also is not important now. I can just minimum value of this one I should find out. Okay, when this value will be minimum. So how to find the minimum of that value? So I want to minimum value of Rs by square root of RL plus square root of RL. Okay, this value I want to find the minimum. Okay, how would you find the minimum of that? So we differentiate this value and then equate it to 0. Okay, so how do you differentiate this? What? I don't know what that is. So let's differentiate it anyway. Okay, Rs is a constant. What is differentiation of 1 by square root of RL? See, Rs, RL to the power of minus half, okay, plus RL to the power of plus half. Okay, so this is same thing. Now differentiate this one. Okay, what is that? Rs is a constant. What is, so minus half minus 3 by 2, okay, plus half RL to the power of 3 by 2. Oh, minus 1 by 2. Okay, so this value should be equal to 0. Okay, so anything you can cancel. So we can cancel half of, okay, for the time being, and then Rs into RL minus 3 by 2 equal to RL into minus 1 by 2. Because this minus is there, I taken it to the other side. Okay, this RL I'll bring it this side. Okay, so it will become plus 3 by 2. Okay, and these two are multiplying. I think somewhere I made a mistake. So 3 by 2 minus half, 1. Okay, oh, I did not make a mistake. Okay, so for this condition, the power is maximum. Okay. That's what we checked also. Okay. So I'm weak at deriving these kind of things. So if these two values are equal, then the power is maximum. Okay. So what is the efficiency? Efficiency is output by input. Okay. So if consider this as a source, this source is sending power. Okay. So how much the power is sending, that is Vs into I load, how much it is received will be V load into I load. Okay. So the supply voltage and the load voltage are not same because there is some voltage drop here. Okay. In fact, the voltage drop will be half, because if these two values are equal, the voltage drop will be half and the efficiency also will be half. Okay. So although you are able to send maximum possible power in this circuit, your efficiency is only 50%. So therefore, when you design that circuit, we don't send the maximum power that way. We just, because of the lesser efficiency. Okay, I think this is about that. So let's jump into one more quick topic, and then with that we can conclude. I think we have half more time. Okay. So the next one was is about some transformations. Sometimes what happens is if the circuit is given like this. Okay. So AB, I'm saying find RAB. Okay. Let's say this is 2, 7, 6, 9, 5, something like this. Okay. How do you find RAB, resistance between A and B? How do you find it? So one thing is you connect this and then you use the ohm meter and then measure it. That's an easy way if you have all the components. But how do you find what is the value of RAB? So there is no series parallel things here. Okay. So 9 and 5 are not parallel. Okay, 9 and 7 are not series. Nothing is series, nothing is parallel. Okay. What? KVL. Okay, I heard one answer KVL, but how do you use KVL to find the resistance between A and B? Okay, current is I. I will also say I equal to 2 amperes. How will you divide it? So this I is 2 amperes because of Kirchhoff's current law applied to entire this thing. Okay. So how do you divide the current? Okay, very good. So this is I1 and this is 2 minus I1. Okay. So that I1 current comes here. Okay, then what happens? So I1 minus I2 and this one will be I2 and then this one 2 minus I1 plus this one. So I1 gets cancelled, 2 minus I2 will be here. Okay. So this 2 minus I2 goes like this, then I2 comes like this. So I2 gets cancelled, 2 amperes is going out. Okay. So we have two unknowns. So where are the two equations? So he's saying connect some battery. Yes? Oh, so even without connecting a battery, he's saying there are two meshes. Now I can use Kirchhoff's voltage law. Okay. What is Kirchhoff's voltage law for this one? I'll start here. Okay. From here I go up. So I am gaining the voltage. Or am I losing the voltage? I am gaining the voltage because this is a high voltage, that's why current is coming. So plus 2I1. Then from here to here nothing. From here to here I am losing the voltage. So minus 6, 2 minus I1. From here to here, how much? Okay, plus 7 I1 minus I2. No, I was thinking what to do after the second equation. Anyway, so this is equal to 0 because we know that in this loop the voltage is 0, there are no voltage sources. Okay. What about this one? So I'll start from here, go up. So plus 9 I2. Okay, from here to here minus 7 I1 minus I2. Okay, from here to here minus 5 2 minus I2 is equal to 0. Okay. So from these two unknowns I can solve it. Okay. Someone wants to try? Since we came up to here, why not just take one more step and then complete it? So how many I2s? I1s? 2 minus into minus plus, 2 plus 6, 8, 8 plus 7, 15. So 15. So is it zeros on the other side? So if it is zeros, then your i's also will be zero. So okay, 12. So we'll come to that. There's only one I2 here. So minus 7 I2. And then what are the constants? 6 into 2, minus 12, goes the other side, plus 12. Okay. And what about this? I1s, minus 7, plus 5. Oh, sorry. This is 2 minus I2. So minus 7. And then what about I2s? 9, 9 plus 7, 16, 16 plus 5, 21. Okay. And then what is this one? 10. Okay. So by the way, we are solving a circuit like this. Okay. So we normally solve the circuit with voltage sources. But what if a current source is given, which is always sending 2 amperes, irrespective of whatever is the thing. But then don't worry about that. So what is the I1, I2 now? So let's do some multiplication. So this is 3 times, isn't it? The first one 3 times, 45, 21, 36. Okay, first row I multiplied 3 times. Then add it. So if I add it, then what I'll get? 45 minus 7, 38. This is 0, I1. So 38 I1 is equal to 46 addition. Okay. So what is I1? 46 by 38. How much is that? How much? Is that correct? Did you? Okay. Okay. So 1.210. And what about this one? I2 is 0.87. Is that so? How did you find I2? You calculated, okay. Whatever. So what is RTH? RAB. See, our first initial problem was find out what is RAB. What is the resistance between A and B? That was our first problem. So yeah, the approach is first we have to find VAB. Okay. So what is VAB? VAB is nothing but Kirchhoff's voltage law from B to A. That is VAB. Okay. So start at B, apply Kirchhoff's voltage law. So nothing is here. Shall we use this path or shall we use this path? So any path we can use. So let's do this one because I1, I2 is there. So from here to here, the current is I2. So what is 9 into 0.87? So 9 into 0.87. So this is positive because I am gaining, and then 2 into 1.21. How much is that? So addition of all of this. What? 10 point? 10.25. Okay. So now what is RAB? Okay. So RAB is VAB by I. I is 2 amperes. So RAB equal to, so this by 2. So 5.125. Okay. So this is one method of calculating the RAB. Okay. So what is the other method? So I accept the value, I'll just take out everything. So the other method is, yeah. So look at this 1, 2, 3 points. Okay. So imagine that there is a device. Okay. that device is having 3 terminals, A, B, C. Okay. So what is inside this device you don't know. Just there are 3 terminals, A, B, C. Okay. The A you are connecting here, B you are connecting here, and C you are connecting here. So something like that. So I just remove all these 3. Do you remember what the values were? Okay, so we'll come back to that. So and then this there is some kind of a device which is like this. Okay. Now inside I can use this kind of connection. But this R1, these 3 resistances R1, R2, R3 are not the earlier resistances. These are something different. Okay. So I convert, the connection was something like this. It's like a delta. This connection I converted to star connection. Okay. By appropriate values, R1, R2, R3, appropriate values, we will calculate how to do that. Now what happens is these 2 are in series. These 2 are in series. So this one branch and this one branch, these 2 are in parallel. Then you add that. Finally, your answer will be 5.125 ohms. Okay. So by converting the delta into star, you can solve this problem. Okay. So that is the second method. We'll do that. Now, before we go forward, I go back to my earlier circuit. It was like this, right? It was like this. Okay. I can also see one star here. Okay. So this star also I can convert to delta. So what I can do is take this point and this point. Okay. Remove all the 3 and then make it into delta. So this is R1, R2, R3, some 3 different values. You have to calculate the equivalent values. Okay. Now what happens? These 2 are in parallel. You can solve that. These 2 are in parallel. You can solve that. Then add them series. So then this is in parallel. Then you can finally find the RAB. So again you get the value 5.125. Okay. That is the third method of doing it. So either delta you convert to star or star you convert to delta, whatever. And then you will observe that you will get series parallel connections. Okay. When you get stuck like that, you have to do the, either you have to write the equations and solve it, that is one method, other method is like this. So what, if you are thinking of, that kind of transformation kind of thing, so let's, so if I mark this as A, B and C, and let's call it R1, R2 and R3. Okay, this is all arbitrary. And this one, some value R small a and then R small b and then R small c. So this is A, B, C. So either your here or here, the behavior should be exactly same. Okay. So I'm just doing a quick derivation actually. So what is RAB? This is resistance between the terminals A and B. C, it is not connected anywhere. Okay. So in this case, what is RAB? So it is by R1 plus R2 plus R3. Okay. So I'll just expand this R3 R1, R3 R2. R3 R1, R3 R2. Okay. RAB is this for this one. Okay. I want the exact same behavior here also. Okay. So what do I get here? RAB, resistance. If I put an ohm meter between A and B and measure the resistance, I'll see what value. Okay, RA plus RB. Because these 2 are in series and this is not connected anywhere, it's fine. So, and this has to be equal. Okay. So let's say this is known values, this is unknown values. Okay. So I want to find out what is RA, RB and all. So because there are 3 unknowns, I need 3 equations. So I'm writing the other equations also. So what is RBC? Resistance between B and C. That will be R2, R3, R2, R1. Okay. R2, R3, R2, R1 by R1 plus R2 plus R3. Okay. So this will be, okay. So between C and A, what is the resistance? R1, R3, R1, R2, and then addition of all. So it is not very difficult, just same thing what you already know. Okay. So what is this one? RA plus RC. Okay. So let's mark the equations. Let's call this, equation X, equation Y, and equation Z. Okay. So if I want RA, then what I'll do is, so X plus Z minus Y. Okay. Add X and Z and then subtract Y. Okay. So RA, 2RA. Okay. 2RA. See, RB minus RB, RC minus RC. This is minus. So that gets cancelled. Okay. So only RA is there, is equal to. So what am I doing? X plus Y minus X plus Z minus Y. Okay. This plus this minus this one. So I will cancel 2, 3. So this term will get cancelled. I'll cancel 2, 1. This term will get cancelled. So remaining term is 3, 1 and 1, 3. Or 2 into R1, R3 divided by R1 plus R2 plus R3, and then 2 also I can cancel. Simple. So this is, right side is known, left side is unknown. You can find the value of RA. Okay. If you look here, see what we are doing is RA is nothing but R1, R3 by the sum of all the three. So this value is nothing but multiplication of these two, division of all the three. Okay. So can you say by that analogy what is RB? So RB equal to R3, R2 divided by R1 plus R2 plus R3. What is RC? So by the way, if you want to calculate using this, what will you do? See, RC is here, RC is here. So Y plus Z minus X. So RA gets cancelled, RB gets cancelled, 2 RC will be here, Y plus Z minus X. So R3, R1 will get cancelled here, R3, R2 will get cancelled here. Only thing is left is R2, R1 and R1, R2. So 2 R2, R1. So that will be R2, R1. 2 is cancelled and then R1 plus R2 plus R3. Okay. So what if this is known and this is unknown? Okay. So it's again a somewhat bigger derivation. I leave it to you to try it out. Okay. Or you can always search in the internet, you will find enough information about the other side also. Okay. So now we have this. We still have time. So what we do is, we'll quickly verify our this one and then we can move forward. Okay. So how do we verify? So this is for what? This is for delta to star. Given delta, you can convert to star. Okay. So what was our first circuit? It was, I remember, it was something like this. So what were the values? This one, this one, this one, 7, this one, 9, 5. Okay. Now I want to do delta to star. Okay. We have two deltas here. This is a delta, this is a delta. Which one shall we convert to star? The above one or below one? What? Which one? Above one? We'll go with that. Okay, so now I want this. Okay. So what is the value of this? 2 into 6 divided by 2 plus 6 plus 7. Okay. 6 plus 2 is 8. 8 plus 7 is 15, okay, 6 into 2 is 12, 12 by 15, 12 by 15, 4 by 5, okay. How much is that? 0.8, okay. Now I want this one. So 14 by 15, 0.93, okay. 7 into 6, 42 divided by 15, okay. 42 divided by 15, 2.8 more decimals, 2.8, that's all. So I can now remove the delta. So why is this formula correct? This formula is correct because we are trying to get the same value of resistance measured across any 2 points. Okay. So 9 plus 0.93. Okay. 9.93. 5 plus 2.8. Okay. 7.8. What next? So these two are parallel. 9.93 into 7.8 divided by that. So how much is that? So 9.93 into 7.8 divided by addition of these two. How much? 4 point? Okay, 4.36. And then I remove this branch and I remove this branch. Okay. 4.36 plus 0.8. How much is that? 5.16 ohms. Okay. So is it same as this one? Why we are not getting exact same value? Because you skipped some of the decimal points. Okay. So these are the other way. So you can use delta to star, you can use star to delta, whatever, and then you can find it out. Okay. So we'll just quickly verify what we are doing here, and then we'll just stop that. So to do that, yesterday we just specially made 2 new components for you. So let's switch to this one. Okay, just refresh this. So you can see this is a device which has 3 terminals. Okay, what is inside this? It may be delta, it may be star, we don't know. Okay, so that is this. I'll keep it, maybe I'll just take this aside. So this is one, okay. Similarly, I have another one. Okay, so which one is star, which one is delta? Okay, suppose I just cover it up, you know. So anyway, just for sake of identification, let's write A here, B here, and C here, so that A here, B here, C here. Now you can tell. You can still you cannot still tell because it looks same. So this is ABC. This is also ABC. Okay. What? Okay. Now we'll try to maybe give some names. So what do you want to call this one and this one? 1 and 2. Can we have some better names instead of calling 1 and 2? See, you might have seen some twins. Okay, so twins have names, no? What? Okay, I hear name Chengu Mangu. So which one is Chengu? This one or this one? Okay. Now I want to measure some resistances. Okay, just for the sake of measurements, let me just quickly. Maybe you can see it like this. I'll just disconnect some of this. Just give me a minute. Yeah. This one will keep it here. So let's take this Shengu and then connect it like this. Okay. Now the other one, maybe I'll just put it here. So I want to find out whether there is any difference between these two. So I'll just keep this for support. Okay. So first, let's measure. What shall we measure? So maybe I'll just write it here. So RAB, RBC, and then RCA. Okay. I need both. So okay, I set it on ohms, and then let's measure here. It's on. So how much are we getting? Okay, 10.09. So let's see here. $10.17. So there are some small variations in the values of the, the resistors which are being manufactured. So I'll write it. Okay. So just to be consistent, I'll write 10.1K, 10.1K. So you can't tell the difference. We are trying to find out, identify the twins actually. So let's try RAC. How much is the value? 7.822. Okay. And what about here? 7.81. Okay. Still very okay. So 7. This one, 82 and then 7.81. So is it reverse? Okay. Okay. Yeah. So let's try BC. So how much is RBC? 11.63. And what about this one? 11.61. Okay. Not very much difference. Okay. So I'll write it 11.6 itself. Okay. So if you ignore the second decimal, it's exactly same. So so what shall we do? How to identify which one is star, which one is delta? So I can try one trick actually. So I can find RA, BC short circuited. Okay, you can do that. So I can find RB with AC short circuited. I can find RC with BA short circuited. Okay, let's try that. Okay. So I'm using this one. So let's try the first one. I am short circuiting B and C, and then I'm short circuiting B and C here also. Now measure the resistance in the first case between this and the short circuited part. Okay. How much is it? 5.931. Okay. So this is 5.9. Okay. 93 actually. So what about this one? I'll just take it and then measure it here. So 5.97 you're getting. Okay. So this is K. In fact, I should not write 9793. Okay. Still it is same, behaving exactly the same way. Okay. So shall we try another combination? AC is short circuited. Okay. So short circuit A and C, just about to reach. Okay. Now, what should I measure, AC or BC? So I'll measure BC. How much I'm getting? 8.88. Okay, let's round it. Okay. Which one was this? This one or Mangu? 8.87. Okay. Or is it 88? I'll change it. We'll change it to 88. So here also I'm short circuiting AC. Now measure the same here. So 8.84. Okay, you can see that. So again it's exactly same. Okay, almost same. So I'll keep it 8.87 only. Okay, so we can't still tell the difference. So, and as you might have guessed, even when I short circuit these two, AB short circuited, here also AB short circuited, and then measure that. How much is that? 6.84. Okay, so this is 6.84. Okay, and then what about here? 6.82. Okay, so I hope you are able to see this clearly in the back. Okay, so is there any other combination I can measure the? See, I have 3 terminals. I can test only with the 3 terminals, and then this is the all combinations we tried, and then we are not able to tell the difference. Okay, so which one is star? Which one is delta? Okay, so let's do one more thing. Maybe I'll just give you some additional information. Okay, so I don't know which one is star, which one is delta, but consider the delta part. Okay, so I'll give you the values of the delta, but which one is delta I don't know. So the values of delta is something like this. So this is 10 kilo ohms, and this is 15 kilo ohms, and this is 22 kilo ohms. A, B and C. Okay, or maybe A, B and C, I don't know. So if this was the delta, can we just verify whether these values are coming correctly or not? Okay, so what is RAB in this? So I'll write it here. So this is delta and this is star. We'll come to star. Okay. So, what is RAB? See, these two are in series. So, it is 37 series with 10. 10 into 37 by 10 plus 37. Okay. 370 by 47. How much is that? 7.87. That means this is C and this is B. Okay. So RAC is how much? 7.87. Okay. Which is almost same as 7.8, 7.8. Okay. So what is RAB? These two are in series. So 32 into 15 divided by 32 plus 15. Fast, I need answers. How much is that? RAB. 10.2. Okay. So we got 10.1 here, 10.1 here, but almost same. So what about RBC? Okay. 25 parallel with 22. How much is that? 25 into 22. So 11.6, 11.6, almost same. Okay. You can even try the other case. See, BC short circuited. So if I short circuit BC, what will happen? So what is RAC? Or RABC? These two are in parallel. So 10 into 15 by 25. How much is that? 6. Okay. So that one, here we are getting 5.93. Okay. This is 5.93. So what about the other one? AC. That means this is short circuited and 15 and 22 will become parallel with the other one. Okay. So 15 into 22 divided by 37. How much is that? 8.91. Okay, so we got 8.84, 8.87. So almost same. Okay. What about the last case? BA. So I short circuit BA and then I measure the resistance between these. 10 and 22 are in parallel. 10 into 22 by 32. How much is that? 6.87. This is almost matching. Okay. So what I kind of proved now is that we have two circuits, Chengu and Mangu. Okay. One of them is delta and that particular delta has a value, these three values. Still we don't know which one because everything is same. So you cannot tell the difference. Okay. So can we convert that to star? So how do you convert this to star? So what is this? So this is again A, B and C. What is this value? 10 into 15 divided by 10 plus 15 plus 22. How much is that? 150 by 47. How much is that? 3 point? So 3.2. What about this? 15 into 22 divided by 47. Fast. 0.2. Okay. So we are just running out of time. Last 5 minutes. Okay. Because we have to see na, what is inside that. So what is this? 4 point. So let's call it 4.7. This is 7.02. So we'll just call it 7. Okay. Now very quickly, what is RAB? Resistance between A and B. These two are in series. 10.2. Okay. Again it is same. So okay, you can't tell the difference. What is RBC? 11.7. Again same. What is CA? 7.9. So 7.87, 7.9, no, 7.8, 7.8. What about this one? See here what we are doing, short circuit BC. Okay, short circuit BC and then find the total resistance. So what is the parallel of these two? 4.7 into 7 divided by that and then add this one. How much is that? 6.01. Okay, which is almost equal to 6. Okay, and this is also 5.9, 5.97. Okay. So what about this one? AC. AC is short circuited. That means these two will become parallel and in series with 7. Okay. So 4.7 into 3.2 divided by 4.7 plus 3.2 plus 7. Total is 8.9. Okay. So we are getting 8.9, 8.9, 8.84, 8.87. All are almost same. Okay. And what about the other case? BA. These two are short circuited. 7 parallel with 3.2. Series with 4.7. How much is that? 6.89. Okay. 6.87, 6.89, 6.84, 6.82. More or less same. Okay. So still you cannot tell the difference which one, but only thing you can tell, what I just gave the information is that what are the components we used. Okay. So yesterday we were going through the lab, find out the combinations of resistors so as to give this kind of measurements. Okay. So these are the measured values, these are the value. But which one is delta, which one is star? So which one is delta, which one is star? So we have these two. Which one is delta, which one is star? So it's you can't tell now. That's the whole point. In the star delta transfer, you cannot, we can't tell the difference. The rest of the circuit cannot tell the difference. Okay? You have a large circuit. Let's say a very big circuit is there. In that big circuit, you take 3 points, and then if it is delta, you can convert to star. If it is star, you can convert to delta. The rest of the circuit cannot tell the difference. So that's the point, because it behaves exactly the same way, whatever you do. Okay? So still, shall we take a guess? So let's take a guess. Which one is star, which one is delta? Okay. So let's check. Okay. So if you are correct, okay, then I'll give you a difficult question paper. If you are wrong, I'll give you a very difficult question paper. Okay. So let's see if you are correct. So I'm opening this. So you can see from this side, you can see only 3 resistors. Again, I am opening this. I'll show it there also. From this side also you can see it looks same from the front. Okay. By the way, this one is Mangu, so I'll just put it like this. Almost done. What happened? So did you get the correct answer? I think you got the correct answer. So this one is here. So, but what are the connections? Just let me quickly show you the connections. Okay, so you are right actually. So this one, if I turn it around, can you see it's star connected. Okay, this is star connected. How can you say it's star connected? The above part is all short circuited and the below parts are taken out. And these resistances, the values are. And what about getting stuck? Let's just wait for the thing to settle. Or maybe I'll just leave it at the back, you can see it. Anyway, I think the video got stuck. So maybe I'll just keep it at the back while going out, you can see. Okay. So with this, I'll stop this part. So is there a class next week? I think you people are having a class, even though it's a midsem week, you are having a class. Okay. So we'll meet next week, Monday class.